Good morning, everyone. Team RFIs present Project SmartCart. My name is Satsani Kampong.
I'm Kevin Eichel.
Andres Flores.
Joseph O'Neill.
And then Ironberg.
NTC.
I'm David Shula, and this project is sponsored by Dr. Zito and the National Science Foundation.
We live in an increasingly profit-driven world. What that means for us in terms of funding is to make a product, or you're either going to have to market it towards the mass population or towards a smaller group that can afford to pay a lot for a certain product, such as the U.S. government. Unfortunately for us, the people we intend to help do not fit into either of these categories. There are approximately 15 million blind or visually impaired people in the United States of America. And thankfully for them and for us, there are organizations such as the National Science Foundation, which can help fund research to benefit such disenfranchised populations. Now, to help people, you can solve a problem for them. A problem that faces many visually impaired people is that they have trouble navigating around unfamiliar places. Of course, solving this problem as a whole would take too much time and more money than we can afford. So we decided to narrow it down to a scope that most of us, or to an area that most of us are familiar with and have to go to on a regular basis. In our case, the grocery store. Now, problems that do face the visually impaired in a grocery store are one, independently locating products, that is finding products by themselves without the aid of a friend or a customer representative, as well as avoiding obstacles in the aisles, whether that be another car, another person, or just things on sale. Our solutions for this are to outfit a shopping cart with a navigation system, as well as a collision warning system. And to go over that briefly is a letter.
This is what a shopping cart would look like when it's outfitted with our SmartCart system. The overall functioning of the system can be broken down into a few simple steps. First, the shopper will be traversing down an aisle, and they would like to locate an object or a product or a place in the store. So the first thing they would do is press the push-to-talk button on the handlebar. The user will then speak the location or product they would wish to be navigated to through the wireless headset. For example, cereal. It is then sent to the backend server, which computes a route from the current location to the location that the user requested. To assist the user further in getting to their specified location, we use collision avoidance. We use sensors to detect objects in front of the cart. If there is an object in close proximity to the cart, the user will be notified via vibration in the handlebars. Now, this will go forward and explain a little bit more on the individual components of the cart.
The separate components of the SmartCart come together to form three separate systems: the navigation system, the collision avoidance system, and the RFID reader system. The collision avoidance system features ultrasonic sensors placed on the front and side of the shopping cart, tied to vibrating motors embedded into the handle of the cart. The navigation system utilizes a wireless headset which communicates to the backend server, and uses the RFID reader system, which features a directional patch antenna on the side of the cart to pick up product IDs. Electrical components and the power supply are featured in the electrical housing on the bottom of the cart rack. The way all these components work together, all these systems work together, will be explained by Kevin.
Okay, so now that we've introduced you to the individual components of our design, here's a block diagram to discuss the relationship between them. As you can see, we will be utilizing two microcontrollers, a primary and a secondary. The primary will be controlling the navigation aspect of our system, and the secondary will be handling the collision avoidance. Driving the primary microcontroller will be an RFID, also using an antenna, as well as a Hall effect sensor to tell the function of when these specific tasks will occur. I'll discuss a little more in depth on that later. The secondary microcontroller will be driven by two ultrasonic sensors as inputs and be output to the user by vibration motors embedded into the handlebar. The two microcontrollers will communicate to each other for two reasons. The primary will tell the secondary when the cart is moving, and the secondary will tell the primary when there is an obstacle in front of the cart. All this information will be in turn sent serially through a wire replacement radio to the backend server. The backend server will house the database as well as the logic for navigating around the store. This in turn will be communicated to the user through a wireless headset and microphone. And now to go into the navigation system will be David.
All right, for our navigation system and for any navigation system, there are three main components you need to know. You need to know what your destination is, you need to know what your current location is, and you need to know the map of the area so you can generate a route to your destination. In terms of the shopping cart, we'll be using the wireless headset to get our destination. We'll be using an RFID reader and RFID tags to determine where in the store we are and what products we're around. And these RFID tags will be stored in a backend server that will be the map of the area. So we'll have a virtual map of the store with these RFID tags. Now, Tatsani will go over the voice communication and how we're going to get our destination into the backend server.
As part of our navigation system, we have the voice communication, which uses the Microsoft as API. That is capable of input text to the speech through the microphone and the headset, and then output the voice recognition. Input the voice recognition through the microphone. We are using the programming language C#, and the voice recognition is speaker independent, which means that you don't have to train the speaker beforehand. For the accuracy, we use the custom lexicon that will limit the dictionary to the certain word that will be used in the grocery store. Now that we have the destination, how do we get the current location? Joe will go into detail that.
Okay, to find your current location, we're using RFID technologies. Now, what does RFID mean? It's short for radio frequency identification. In order for the system to work, there needs to be two main components. One which is the RFID reader and the antenna represented on the left. The other one being the RFID tag represented on the right. What happens is the RFID reader through the antenna pulses out energy, which is then captured by the antenna of the RFID tag. This induces a small voltage which activates its microcontroller. The RFID tag in turn pulses back energy, which transmits data to the RFID reader. This is, for us, going to be a unique serial number. And due to the distance constraints, we'll be able to determine your location using pre-placed tags. And knowing which tag you scan last, we'll be able to estimate approximately where you are. To go over our hardware in more detail is Vinti.
Now, since stores have relatively wide aisles, we needed an RFID system that could read a good amount of distance. We decided on the SkyTech M10 RFID reader with the directional antenna and the Alien Higgs Squiggle passive RFID tags. With this setup, we were able to obtain 3 feet of reliable reading range. We decided on the reader since it operates in the ultra-high frequency range of 902 megahertz and 928 megahertz, which provided that extra extended range we need compared to other RFID readers, as well as it operates at 3.3 volts, which it uses low power, and it's relatively small and compact, which gives us that portability function that we need. Now for the tags, we decided with the Alien Higgs Squiggle tags, since they're small, running about 4 inches in length and a ½ inch in width, which is perfect to mount on store shelves. They're also passive, which Joe stated uses no power, which is easy to maintain and replace if any of the tags were broken or needed repair. And they're also writable tags, since this allows stores to customize their own unique identification number to make the ease of use and implementation of the tag. Now Andreas will go over the collision avoidance system.